So, and a multilinear polynomial is a polynomial such that individual degrees are at most 1. Every variable either doesn't appear or appears with degree at most 1. So some examples, it's this. So example is maybe a simple example is x1 times x2 plus x3. This is multilinear, simple example. More complicated is the determinant, which was already defined, the permanent, which was also already defined. All of these are multilinear. And another example, which I will also talk about, is iterated matrix multiplication that was mentioned before. And iterated matrix multiplication, we have, let's say, n matrices, each n by n. We want to multiply all of them. This gives us n squared polynomials, but we can think of, say, the first entry of this multiplication. So we look at a1 times a2 up to an. This is a matrix, and we look on this polynomial. So these are examples of multilinear polynomials. And we want to compute them, and the method our options to compute, so the model, or the models of computation will first be circuits. It's very difficult. Is it because it's behind the main? So the first model is circuits, it's already defined. We'll have also formulas. These are when the circuits are actually trees. And I will also discuss a third model that was not discussed so far, which is an arithmetic branching program. And I will call it, in short, ABPs, arithmetic branching program. It was a mistake. So circuits and formulas we saw already today, so I will not define them. And I will define branching program by a picture. So an arithmetic branching program is a directed acyclic graph with special two vertices, S and T. So the edges are somewhere here, going from place to place. And there are no cycles. And on every edge, there is a label of an edge that is either a field element or some variable. Okay, so we just label all the vertices of this graph by field elements or variables. And now, how does this compute a polynomial? So arithmetic branching program computes as follows. So first, every path in the program from S to T computes a monomial. So if gamma is the path from S to T, then the polynomial that gamma computes is the product of all the things along it, all the edges along it, of the label of the edge. This is what a path computes. And the program is just computes the sum of all over all passes, the polynomial the path computes. So this is how these things compute polynomials. And it's fairly easy to see that such a computation is basically an iterated matrix multiplication with certain matrices. And so these are the three models of computation. And now we will, so maybe just to put things in perspective, so we always have the formulas are weaker than arithmetic branching programs, which are weaker than circuits. So this means that one can simulate the other efficiently. And we want to try to understand, is this equality or inequality, is this equality or inequality, things like that. And so this is the model of computation. And because, I want to talk about the multilinear world. And in the multilinear world, there are multilinear circuits. These are specific circuits that compute multilinear polynomials. There are multilinear formulas and multilinear arithmetic branching programs. So there are multilinear analogs or versions of computation models. And I do not want to discuss it in great detail, but there are two options to define multilinearity. There is a semantic meaning of meaning option, where you just look on the, say, every sub-computation in the circuit and require the sub-computation to be multilinear. This is semantic. And there is a syntactic definition when you require things to formally be multilinear. So in a syntactic way, you just look on it and it must be multilinear. So we will focus, we consider the syntactic definition of multilinearity, and I will give, for example, the syntactic definition of ABPs. For example, ABP is multilinear if the monomial F gamma, all the monomials that appear are multilinear. So if we go along a path from S to T, we never see a variable twice. Okay, so this is, for example, this version of multilinearity, and there are also these two options. So you're very quiet. Is it clear? You want to ask questions? Yes. Thanks. So I let them be field elements and variables. You can do other things if you want. So maybe I will give an example. So this is S, this is T. So this is an example of a branching program, and the polynomial it computes is x1 times x2 plus x3 plus 2x3. And if this is this, there are no colors, so we can also add, say, an edge here and label it by something, then it will make the computation more complicated. So this is the model. And now we want to try to prove lower bounds for these things. So this is the so we want find polynomial f such that every multilinear device, either a circuit, a formula, a branching program, something like this, that computing this, must be large. This is what we want to do. And I will first state a few results of this form that most of them Amir already stated, I think. So theorems of this type, some lower bound. So run RAG shows that the formula size of permanent is at least n to the log n over 100 or n by n matrix. All the formulas, branching program, everything now is multilinear. So this was a very big step in our understanding of multilinear computation. So this is a quasi-polynomial lower. Then later on, he realized, and then there are some simplifications perhaps, that there is f with n variables. So this is a slightly more sophisticated statement. Not only that the determinant and permanent cannot be computed efficiently, there is a polynomial f that has circuits of size linear, very small circuit, but every formula this is a more delicate statement, but it also teaches us a lot. So this, for example, tells us that in the multilinear world, one of these inequalities is a strict inequality. So circuits are not formulas. They are strictly stronger than formulas. Okay? There is a small circuit, but every formula must be pretty large. And maybe some comments about this. So, is it clear? So, first comment is that what the depth reduction showed us, the VSBR statement, applied in the multilinear world, says that this is tight. This is one perspective. Every polynomial that has such a small circuit has a formula of roughly this size. This is what VSBR tells us. And another thing that VSBR tells us, or that this actually tells us about VSBR, if every depth reduction that preserves multilinearity, if there is some procedure that takes a multilinear circuit and reduces its depth, so it preserves, but if the original circuit is multilinear, then the new circuit is also multilinear, must cause superpolynomial blow-up. So this is because there is a small circuit that the formula size must be huge. So, so here I defined what is a multilinear branching program. So a multilinear circuit, maybe I will define it. It's a circuit, so a multilinear circuit. It's a circuit that if we have some place that multiplies at some position in the circuit, we multiply two polynomials. So it is a gate which is a multiplication of two other gates. Then the variables that appear in the first gate are disjoint from the variables that appear in the second gate. So every multiplication is between two disjoint sets of variables. So this is the syntactic definition I mentioned before. And yeah, and this circuit is multilinear in that sense, and everything here is multilinear in that sense. So and now I want to, is it okay? And now I want to explain, and there are more. There are results for constant depth that are more, like the lower bounds are stronger than this, and for circuits also there is some lower bound that Amir mentioned. And maybe I want to mention in this context that quite recently, together with Ernst Beer, Guillaume Maloud, Sylvain Perifel, instead of a circuit of this size, one can write a branching program. Again, multilinear branching program, again of this size, linear doesn't matter. And so this is a stronger statement that tells us that here in the multilinear world there is inequality. And so this is roughly what is known about this diagram today in the multilinear setting. And I want to now explain how to prove. How do you prove all of these things? So of course I will not explain how to prove everything here, but I want to give you some of the ideas that go into the proof, and they are related to what we have already seen. So there are two parts to the proof. the proof of such things. So the first part, one way to think about it in the context we saw so far is depth reduction, depth-4 reduction. This is not the language it was stated in, and Ankit will tell us much more about this. But I just think about it as a structural statement. So we just find some structure that we can use. This is the first part, and it's roughly like this. It's roughly like this. It's a theorem of this form. It says that if f is easy, where easy is some quantitative statement, then this, for example, we saw a specific example in the monotone setting, but it works in general. Then we can write f as the sum of things that have some property. So it's easy. So S is small. It's not a sum of too many things. And Fi are structured. And there is some specific structure that we potentially want to use. And to understand what is the meaning of the structure depends on the model that we consider. Something else. No, this is the first part. Okay, we take the polynomial that is supposedly easy, and we write it in this way. And the second part is to prove find f such that S must be large. This is the second step. We just want to find some polynomial that if we want to write it as in this way, we just can't with if we want to use a short sum. And usually, if we find one f, usually we find many f's. So it's actually, it may be finding some family of polynomials. Or in another way, that S must be large, or finding some property of polynomial that guarantees that S is large. So this is roughly the two parts of the proof. And for example, the first part will be this statement, the lower bound for determinant permanent. What is the structure in the case of multilinear computation. So for multilinear computation, we have the following how do you say, specific, this is a specific case of this general phenomenon. So it's a, let's call it a lemma or theorem. It says that if F has multilinear formula of size smaller than F, then we can write F indeed as a short sum of other polynomials, and exactly as it is written there. And this set of polynomials is inside a structured set of polynomials that I will define G. This is the structured set of polynomials. So what is G? G is the set of all polynomials. Okay? I'm just defining a family of polynomials. So it's a family of polynomials. They can be written as G1 times G2 up to GT. Okay, they are a product of many things, and the structure is that we can partition the variables to T parts. This is a disjoint union. We break the variables to T parts, where each GI is a polynomial in Xi. So each one of the how do you say, you break a number into its factors. Yes, thank you. Each factor of G is a polynomial in the corresponding set of variables, and this is one property. This holds this for every I. The other property is that these sets are not too small. If they are small, it's meaningless. So they are of size n, say, to the 1 over 100. This is, you can write it basically whatever you want, any constant. And the third property is that if t is 1, then again we didn't achieve anything. So the third property is that t is large. It's at least log n over 100. Okay, so this is the structured family of polynomials. It's a product of many things, each non-trivial. This guarantees the non-trivial. So this is the structured theorem, and it's very easy to prove. It's much more easier than what Nired showed. It's really an exercise. Maybe the only thing it uses combinatorially is that in a tree, in a binary tree, there is a vertex inside the tree that underneath it roughly half of the tree lies. This is the combinatorial essence of this lemma. It's simple. And so this is the structure part. We found some structure. And now we want to use this. Yes. So I can keep on going. Okay. Thank you. Yes, yes. Yeah, this G is multilinear. The second step is how to use this structure. And this again, so this was not in Ran's original language. It's in a slightly different language, which I think is clearer and also fits well the depth reduction that is common today. This part was the main idea. So the property that is good against such a structure is called the full rank. Okay? This is the name. The polynomial, it's a property of polynomials. So I want to define this property that will guarantee a lower bound. And to do this, I have to first define a definition given a polynomial h. Now, in two disjoint sets of variables, okay, so the polynomial h has two names to the variables, y and z, and we can define a matrix, M of h, and it's a matrix such that M of h in a position P and Q. P is a monomial in Y, and Q is a monomial in Z. So we take the polynomial, we partition the monomials according to the Y part and Z part. So in the position P and Q, it's the coefficient of PQ in H. So we took the vector that is the polynomial and rearranged it in a matrix. So let's see an example. It's a very simple matrix. So an example, if H is 1 plus Y1, Z1, it's one polynomial of this form, then M of H, so the rows of the matrix M are labeled by monomials in Y, which are Y1 and Y1. The columns are by monomials in Z. In the position 1, 1, the coefficient is 1. In the position Z1, it's 0, 0, and 1. So this polynomial corresponds to the identity matrix. So this is the partial derivative matrix. And with it, we will define a polynomial in variables x as a full rank polynomial in the following way. F, so this is another definition. F in the variables x is full rank. And if we partition of the variables x to two parts, y and z, of equal size, so it doesn't matter how we partition the variables to two parts, y and z, the rank of the matrix we get, so we can apply this partition to the polynomial f. So we just rename part of the variables as y and parts of the other part of the variable in z. We get a polynomial fa in the variables y and z that corresponds to the partition A. The rank of this matrix is full. So is it clear what is the definition? If you have questions, please ask. So this is a property of polynomials. It's a family of polynomials. Every polynomial that satisfies this, we call it a full a full rank polynomial, and the theorem that makes this useful, that again, basically one proof, is that if f can be written as in this way, fi in G, in the same structured polynomial, and S is smaller than n to the log n over 100, so not too many, a sum of not too many things, then f is not full rank. Okay, this was the main theorem. We use a structure and the property together to get a lower bound. So if f is full rank, S must be large. Okay? And now the real essence of this approach, the reason we can handle the multilinear case so in relatively good success, is that the proof of this theorem is not algebraic at all, or it uses very, very little algebra. It's mostly combinatorics. We deal with sets. We don't deal with polynomials. This is part of the reason this is a possibility. And now I want to explain how to roughly prove such a theorem. So the theorem follows from, I call it a lemma. And the lemma addresses a single polynomial that is structured. It says something like this. If we have a polynomial in G, a structured polynomial, and we choose A at random. So out of all the n choose two ways to partition x to y and z, we choose one uniformly at random. Then the probability that the rank, the matrix we get, so we apply this partition to G and then look in the partial derivative matrix N, the probability that this rank is high, I'll put it like this, that it's almost full. The probability that the rank, a full rank matrix is 2 to the n over 2. This is a multilinear polynomial. The total number of monomials is 2 to the n. When we partition it to a square matrix, there are 2 to the n over 2 rows and 2 to the n over 2 columns. So without this, it would be full rank. The lemma says that the probability that the rank is high, is close to being full rank, is very small. It's 2 to the minus, n to the minus log n. And roughly, again, there is over 100. Okay, this is the lemma that proves the theorem. First, I will show how the lemma implies the theorem, and then I will explain why the lemma is very simple combinatorics. So the lemma implies the theorem in the following. So once we see how the lemma implies the theorem, it remains to prove the lemma in order to sort of get understanding of the lower bound. So how does the lemma imply the theorem? So it's very simple. So we know the lemma, we want to prove the theorem. So we do the other way. Assume, or let f be f I as is written there, and s is small. So we choose such a polynomial, and we want to say that it is not of full rank. So what do? We have the lemma, so choose A at random. Okay? This is what we'll do. Just choose completely at random a partition, and we want to see the probability that M of f of A is full. Okay? We want to prove about this number just that it is smaller than 1. In the second it's smaller than 1, there is some A for which it's not full. Okay, so let's prove that it is smaller than 1. So first, we use this structure of f. F is a sum of fi. So we just want to prove that the probability that the sum of m of fi of A is full. So f is this sum, and the partial derivative matrix is additive. The partial derivative matrix of a sum is the sum of matrices. I just use this. Now, instead of this, the only way this rank will be full, so I will write it, this is at most the probability that there exists some I such that the rank of M f I of A is at least 2 to the n over 2 over 100. So I want to say, if, look on it on the other side, I want to say that the complement of this is contained in the complement of this. What does it mean? If for every I the rank is small, then with some matrices of small rank, we can get a matrix of full rank. So if for every I the rank is, so this means that this event is contained in this event. Okay? So, and this, here we only use that S is smaller than n 2 to the n to the 1 over 100. Here we didn't use a lot about S, just that there are no really exponentially many matrices, right? Because the gap here from full rank is huge comparatively. Is it clear? Okay. And now we use a union bound. This is at most S, sum from 1 to S, the probability that the rank so that we just use a union bound. We take the existential quantifier out. And now this is at most S times n to the minus log n. This is what the lemma tells us. But S is not large. S is at most n to the log n. So overall, this is smaller than 1. Okay? This is much smaller than 1 if S is chosen carefully. Okay, so this simple lemma, the lemma allows us to argue just about a specific polynomial, and from it we deduce relatively simply a lower bound. Can I erase this? So beautiful. So, okay, so all that we need to do now to see the whole proof, or a little bit feel the proof, the ideas behind the proof is to prove this lemma. Right? Right? This is what separates us from truth. So let's try to argue proof sketch of lemma. So we have a polynomial g that is a product. Let's write it here, it's written here. G is a product of log n field, or at least log n field. Each one is pretty large. So let's write the variables in this way. There is x1, and then there is x2, and then there is x3, and then there is xp. So I just wrote the variables in this specific order. This comes with the fact that G is a structure polynomial in capital G. Okay, now we choose A at random. We partition the variables to two parts at random. What does this correspond to? We write here, this is y1 and this is z1. We partition x1 to two parts at random. And we also partition x2 to two parts at random. And x3 to two parts at random. And xt to two parts at random. Right? This is the meaning of choosing a partition at random. And what do we and the main observation that is purely the main observation is that the information in this picture is all we need. There is no more algebra in here. Okay, once we understand this picture, which is like it's very simple combinatorics, we finish the proof. So the observation if the size of y, say y1, is not close to the size of z1, so not close will be, say, like this. If there is some difference between the size of y1 and z1, okay, so there are a little bit more y's than z's in the first part, then the rank of mga is at most 2 to the n over 2 minus this. Okay, this is the main observation. If in this picture there are slightly more y's than z's in one of the buckets, we are done. Okay, why is this true? So we need to see two more things. Why is this observation true? And why does this observation imply the lemma? So first, let's see why is this true. And the basic reason that this is true is that the rank of A by B matrix, if we have any matrix with A rows and B columns, it has a very strange property. It's at most the minimum between A and B. Okay, this is the property that of rank. It's a strange property that minimum, it's a very incontinuous operation minimum. Like it's a strange quantity, but still this is like, it's trivial. And the minute we see this here, once we have a difference between the y's and z's, this means that the matrix is not balanced. There are much more rows than columns or vice versa. So instead of being the average of, so the matrix to be of full rank, it has to be of size mg1 of A is full rank only when the size of y1 is the size of z1, right? Otherwise, it cannot have what the potential rank it should have. And here it says not only that they are not equal, they're even far away. So we get a quantitative improvement. Okay? So this is the explanation of the observation. And now with this observation, we just need to understand if we partition log n buckets at random to two parts, what is the probability that in all of them we get exactly 1/2? We can't deviate from 1/2 at all. So now the probability that n of GA has rank more than 2 to the n raised to minus 10 to the epsilon. And for this to happen, it must be that for every I from 1 to t, the size of yi minus the size of zi is smaller than n to the 100, n to the epsilon, sorry. The only way the rank is full if all of them are close. Here there is maybe a slight amount of thinking to do to see how the other things contribute. So there is a small gap here. I will not explain. It's very simple. But roughly we said that in G1, if this is true, in G1 we lost. And the statement is if we lost once, that's it. We can't gain it again. And so this is a small d. And now we have t events. What is the probability that this happens in one specific coordinate? So I want to say that this is roughly the probability that this happens in the first coordinate, but roughly raised to the power of t. Now this is not really correct, so I will write it like this. But I want to say that because these sets are disjoint, x1 is disjoint than x2, then all of these events are roughly independent. Numerically, they are independent. So the probability of the intersection is the product of the probabilities, which is roughly this thing. And now what is the probability that this holds for a single, for x1? So this is roughly n to the epsilon times 2 over, so for this to hold, the difference is a number. The difference between the size of y1 and z1 is a number. It's minus n to the epsilon, minus n to the epsilon plus 1. There are 2 to the n to the epsilon values the difference can take. What is the probability that a given value will be taken? It's x1 to the size 1/2. This is the middle binomial coefficient. The middle binomial coefficient is the largest, and it's roughly of size this compared to the whole thing. Okay, so this is a simple calculation overall. And I'm sure you can. So this is roughly correct. Numerically, it's correct. And now we are guaranteed that these x's are large. They are much more than n to the epsilon. There are n to the, say, 1/4. So overall, this is roughly n to the minus t with 100 here. And this is exactly what we wanted. Okay? I think this is enough details for this late hour. So I'll just so what was the proof? There are many things written. So we had some structure, this structure, every formula, we found some structure inside it, and then we found some property that violates this structure. We called it full rank, and somehow all of the algebraic computations, like circuits, formulas, all of this, translated to a relatively simple combinatorics. And this is the reason multilinear world is easier. We do combinatorics, we don't do algebraic geometry. I just want, so this was roughly the proof. I want to finish with one question that I also think combinatorics can address, but I don't know how to do it. So just to conclude with one open question, is it true that ABPs are strictly weaker than circuits in the multilinear case? So we have a way to prove formula lower bounds. We don't have a way so far to prove branching programs lower bounds in the multilinear setting, and I think there is something new to, to prove this. There is some new idea that is needed, but I don't know how to do it, so I can't really say. So do you have more questions? Yes. Not a good one, not a good enough one. You can do some things, but I think they're not good enough. At least I don't know how to use them. Yes. What? So again, everything is like a short sum. And in this case, it will be, say, the number of variables in Fi is equal to the number of variables in Gi. Okay, so this is one example of a structure. You just break the variables exactly to two parts. Okay, so a short sum of this. A random polynomial will never have small f, so it's good enough for lower bounds. But for me, it's too weak of a structure to use. I don't know how to use this. In the arithmetic world, no. I don't know also about, this is an easier question. Yeah. So Shrikant is saying prove any lower bounds for ADP, not even for circuits. Yeah, this I also don't know. Mm-hmm. Yeah, it's a good question. Yeah, to complete this, of course, we need to find some f that has full rank. So to prove that the determinant and permanent have full rank, this requires some work. And they are not full rank in this sense, in some weaker sense. But to construct a polynomial of full rank, it's fairly easy. You basically do it by induction. You have a polynomial with two variables. It's easy to construct. And then you just add at every step two more variables to the number of variables in a way that guarantees that everything is okay. It's relatively straightforward, but I think by a small circuit, yes. Mm-hmm. This is multilinear.